In this video, we're going to be going over the pH scale and also calculations regarding pH. So, the acidity of a solution depends on the concentration of hydrogen or hydronium, if we're talking about Arrhenius modified definition of acids. Or hydronium ions in solution. We usually measure acidity using the pH scale. So just as a quick reminder here, for the pH scale, it ranges from 0 to 14, with 7 in the middle, meaning that a solution with a pH of 7 right on the dot is going to be neutral. Anything that is less than 7 is going to be acidic. And anything more than 7, or a pH of 7, is going to be basic. Okay. So pHs also kind of correlate to the concentration of hydronium ions. So if you have a solution that is acidic, it's going to have a hydronium ion concentration that is greater than 1 times 10 to the power of -7. Okay, and if you have a basic solution, it will have a hydronium ion concentration that is less than 1 times 10 to the power of -7. So that's what these pieces right here are meaning. And that will be in moles per liter. Okay, so what I wrote out here is just what this part's saying. Meanwhile, basic solutions will have a hydronium ion concentration less than 1 times 10 to the power of -7 moles per liter. So that's what this part is saying here. So hydronium ions are responsible for the properties of acids. The higher the hydronium ion concentration, that's what this means right here. So anytime you see square brackets, it's talking about the concentration of and then whatever's inside the square brackets. So the higher the concentration of hydronium ions, the more acidic a solution becomes. So for example, if we had a hydronium ion concentration equal to 1 times 10 to the -7, which if we weren't writing that in scientific notation, that would just be 0.1 mole per liter. It is a stronger acid than a solution that has a concentration of hydronium ions equal to 1 times 10 to the -6. Okay, so just as a reminder here, the bigger the concentration of hydronium, the more acidic it's going to be. Okay, so since this number is bigger than this number, that's why we can say this is a stronger acid than this solution, because the first one has a higher concentration of hydronium ions compared to the second one here. Okay, so higher concentration. No, that wasn't very neat. Of hydronium versus this is a lower concentration of hydronium. Oop. Okay, so sometimes students will struggle with like how to figure out if a number is bigger than or smaller than when they're using scientific notation. So what I'd recommend to help you out is first focus on what the exponent is. So since -1 is a bigger number than -6, that's how you can tell that this number is bigger than this number, okay? If the exponents happen to be the same, so let's say we had a value of, I don't know, 5.0 times 10 to the power of -4 versus 3 times 10 to the power of -4. So mole per liter, I should put my units. So now we got to ask ourselves, okay, what would be the bigger of these two numbers? So the exponents, they are exactly the same. So we can't rely on that to tell us which number is bigger or which solution has the bigger concentration of hydronium ions in this case. So if that is the case, then you got to move on to looking at the number out in front. Okay, so then you can say, well, 5 is bigger than 3, therefore the solution with the concentration of 5 times 10 to the -4 is going to have the higher concentration of hydronium. So let's just add in hydronium. Is equal to that. So this is the higher concentration one versus, I'll just move over the versus. And have to squeeze in the equal sign there. Okay, so this is going to be a lower concentration. So the solution with the higher concentration, it's going to be more acidic. So before we move on, let's make sure to highlight this because it is important here. Now pH, all that means is just the power of hydrogen. So this next point is just saying that for hydronium concentrations for acids, typically you're going to have it to some negative exponent, or some base 10 to a negative exponent. Okay, and the pH scale, it's going to go from 0 to 14, as we have said before. Okay. Now, if the concentration of hydronium ions goes up, then the pH goes down, and the solution becomes more acidic. Whereas, if the concentration of hydronium ions goes down, then the pH is going to increase and the solution becomes less acidic, or you could also think of it as becoming more basic. Okay, so a nice visual for like what's in this box here is, I'm going to draw it over to the left here. So let's say we've got a rectangle here, and it's representing our pH from 0, so very acidic, to basic, being 14. So this is acidic, this is basic. Okay, and what we're going to do is we're going to draw a line here, a diagonal line. Alright, so this is just a visual representation of what this box is saying. So when we have a big concentration of hydronium, so I'm going to write hydronium quite large here. So when we have a big concentration of hydronium, that's why I drew hydronium quite large, it's going to be quite acidic. Okay? Whereas if we have a small concentration of hydronium, so that's why I'm drawing it small, your solution is going to be basic. And maybe I'll write a little 7 in here. And the opposite is going to be true for hydroxide ions. So if you have a large concentration of hydroxide ions, your solution is going to be basic. That's why I'm drawing the hydroxide ion quite large. If you have a very small concentration of hydroxide ions, then your solution is going to be quite acidic. Okay, so just so that you know, like all acidic or basic solutions do have some degree of concentration of hydronium ions as well as hydroxide ions, and how much you have determines how acidic or basic your solution is. Typically, we tend to focus on the concentration of hydronium, but also the concentration of hydroxide can determine how basic your solution is. Okay? So this is important to know, and it is important to be able to keep it straight that, okay, when concentration of hydronium goes up, pH goes down. And it's kind of counterintuitive because one goes up, the other one goes down. So make sure that you get this in your head. Okay, so that's why I find this diagram is very helpful to keep things straight with the concentration of hydronium versus concentration of hydroxide and what that means in terms of an acidic or basic solution. All right, so as a summary with what we just talked about, acidic solutions are going to have a concentration of hydronium that is greater than 1 times 10 to the power of negative 7, and their pH will be less than 7. A neutral solution will have a hydronium ion concentration exactly equal to 1 times 10 to the negative 7. Okay, and the pH will be exactly 7. If it is off from these values, then it cannot be a truly neutral solution. A basic solution will have a hydronium ion concentration of less than 1 times 10 to the negative 7 and a pH greater than 7. So here we've got some practice. So I'm just going to do the first two here. So we've got a hydronium ion concentration of 2.4 times 10 to the negative 5. All right, so we need to decide, is this number bigger or smaller than, we'll just go with this number to figure out if it's acidic or basic, because we know it's not going to be neutral because it's not exactly this number. All right, so 2.4 times 10 to the negative 5. Let's compare our exponents here. So negative 5 is a bigger value than negative 7. So that means that this number is a bigger number than 1 times 10 to the power of negative 7. Okay, because negative 5 is more positive than negative 7. So that means that this is going to be acidic. So I'm going to write A for acidic, N for neutral, B for basic. So this will be acidic. Okay? Whereas if we look at this number over here, well, negative 8, that is smaller than negative 7. So that means that it can't be acidic. It has to be basic because our basic solutions have a hydronium concentration less than 1 times 10 to the negative 7. So for basic solutions, you're looking for a smaller number, okay, or a more negative exponent. So this right here will be basic. Okay, pH, I find kiddos have a pretty easy time with figuring out pH, because you're looking for, is it either less than 7, that would be acidic, equal to 7, that would be neutral, or greater than 7. Okay, so make sure you finish these practice questions. Now, since the pH scale is logarithmic, what this means is that anytime your pH changes by 1, that means your concentration of hydronium, that should say, hydronium ions, changes by a factor of 10. Okay, so this is the acidic side to our pH scale. This is the basic side. So let's say we had a solution that started at a pH of 7. Okay, and let's say the pH of it decreased to a pH of 4, let's say. So it went 1, 2, 3. Okay, so every time we're moving a pH unit, your concentration of hydronium is going to change by 10 times. Okay, so this is going to be 10 times 10 times 10. That's equal to 1,000. Okay, so this is 1,000 times. Now we got to decide if our hydronium concentration is increasing or decreasing. So remember that when our solutions become more acidic, our hydronium ion concentration is going to be increasing. And actually, you know what would be better? This diagram's actually better. So the further to the acidic side we go, the greater the hydronium ion concentration. All right, so that means it's going to be 1,000 times increase in the concentration of hydronium. Whereas, let's say we had a solution that started out with a pH of 10 and went up to 12. So again, this is tenfold increase every time you change a pH unit. So 10 times 10, that's going to be equal to 100. So it's 100 times decrease because we're becoming more basic. Decrease in hydronium ion concentration. Okay, so to go back to our visual here, the more basic you become, the smaller the concentration of hydronium ions that you have. Okay, so with our question over here, how much more acidic is something with a pH of 4 compared to something with a pH of 7? Well, we kind of already answered that here. Okay, so something with a pH of 4 is going to have 1,000 times higher concentration of hydronium compared to a solution with a pH of 7. So we kind of already answered that right here. So it's just going to be 1,000 times more acidic. Okay, so if you're wondering what this is right here, this is a summary of all of the formulas that we are going to be using to figure out pH, pOH, hydronium concentration, as well as hydroxide concentration. We will get to that in a little bit here. Okay, but first we need to talk about significant digits and pH, because the significant digits are a little bit weird compared to how we have been operating. Okay, so the number of decimal places in pH is going to be equal to the number of significant digits for the hydronium ion concentration. Okay, so likewise, the number of significant digits of the hydronium ion concentration is going to be equal to the number of decimal places in pH. Okay, so Another way to say this is when reporting pH values, only the digits to the right of the decimal are considered significant. Okay, so how I like to summarize this is for pH as well as pOH once we get there, but pH and pOH, they both have a P in them. Okay, so you're always looking after the point, emphasis on the P in point. You're always looking after the point for your significant digits for pOH and pH. So for example, a pH of 8.29 has 2 significant digits because there's 2 digits after the point in this value. Whereas a pH of 3 has 0 significant digits because there's no digits after the decimal point in that value. Okay, so let's get started with a couple of these. So a pH of 10.01. So since it's pH, it has a P in it. We're looking after the point. So this has 2 significant digits. Okay, because these zeros right here, they're sandwich zeros, so they're in between 2 digits that are not 0. That's why I call them sandwich zeros. So they are significant. Okay, as a reminder, sandwich zeros and trailing zeros, so trailing zeros are any zero that comes after a non-zero digit, both of those are significant. Leading zeros, so any zero before some non-zero digit, so these would be leading zeros, these are not significant. So that's just a quick refresher for significant digits. Okay, now let's look at this. So this is a concentration value. The word concentration does not have the letter P in it. So that means you're looking at the entire number, not just the digits after the decimal. Okay, so these are leading zeros, so they don't count for significant digits, but these do count. So this has 2 significant digits. Okay, so make sure you give the rest of these a try here. So you can pause the video and give them a try. All right, so if you have your values or the amount of sigdigs for all of these questions here, I'm just going to go through them quickly. Okay, so I'll be highlighting where the sigdigs are. So pH here, so that's 1 sigdig. For the next 2, there's where the sigdigs are. So pH, look after the point. So this has 2 sigdigs and this has 1 sigdig. Now for these other values here, these are concentration values. So the word concentration does not have the letter P in it, so we're looking at the entire number here, and this is where we're looking for sigdigs. Okay, so this has 3 sigdigs, 2 sigdigs, and then 3 sigdigs. Quick rules for sigdigs for pH and concentration. pH, look after the point. Okay, and for pH also, there's not going to be any units. Whereas for concentration, the units are, from here on out, they're pretty much always going to be moles per liter. And for concentration, we're using our normal sigdig rules where you're looking at the entire number. Okay, but let's write out what I said earlier, because it's not just going to cover pH, but also pOH. So anything with a P in it, so pH or pOH, so pH is just power of hydrogen, pOH is the power of hydroxide, has sigdigs after the point. So by this I mean the decimal point. Okay, so extra emphasis on the P for all of this here. And then for concentration, that word does not have the letter P, so you look at the whole word, or the whole number. All right, just before we move on, if you are wondering why for these values we're only looking here and we're not including this in the sig digs, the times 10 to the power of whatever, that's only telling you how many spots to move the decimal place in order to go from scientific notation to like regular notation for writing out a number there. Okay, so that's why you're only pay attention to what I've highlighted in blue here for the sig digs. All right, moving on to calculating pH. So this is an important formula for calculating pH. So it says that we're going to find pH if we take the negative log of the concentration of hydronium. So oftentimes the things that or the thing that causes students the most grief is forgetting the negative. So don't forget the negative. So if you get a weird number for pH, you probably forgot the negative. So for example here, we're given a hydronium ion concentration of 2.2 times 10 to the power of negative 7. What is the pH? So this is what it would look like if you put it in your calculator here. So just to show you what that would look like there, I brought up my own calculator here. So what you would do is go negative and then log. So and then concentration of hydronium, so 2.27. And then to get the times 10 part, you would go second function log, and then negative 7. And then I'm just going to click the right arrow just to get out of here, close the bracket, hit enter, and that's how you would do it. Okay. So for this, you go second function, and then log to get that times 10 to the power of, and then whatever. Okay, and then just as another reminder here, the square brackets just mean concentration of, and then whatever's inside of the square brackets. Oop. Okay, so if we were writing this, what I would expect that you show for your work would be negative log and then 2.27 times 10 to the power of negative 7. And then from our answer here, like I'm just going to write, I'm not going to round it just yet, so I'm just going to go to the first 4 digits after the decimal, 39 ... Okay, so since this is concentration, this has 3 sig digs. So now our pH value has to have 3 sig digs. So remember, pH has a P in it, so we're looking after the point. So our sig digs are going to start counting here. So 1, 2, 3. There's our cutoff line. So pH is equal to 6.644. And I don't need to rate any units because pH does not have any units. All right, so example 1. What is the pH of a solution that has a hydronium ion concentration of 5.1 times 10 to the negative 6? So first things first, always write out your formula. So pH is equal to negative log concentration of hydronium. Okay, and then we're going to plug in our value that we got. So negative log 5.1 times 10 to the negative 6. So on my calculator, how I'd write this is negative log 5.1 times 10 to the negative 6. Hit enter. So I get 5.2924, keeps on going on forever. Dot, 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 just means it keeps on going on forever. Okay, so looking at our original number, so 5.1, that has 2 sig digs to it because it's a value of concentration. So that means my pH value also has to have 2 sig digs. So pH, look after the point, 1, 2, there's my cutoff line. So pH is equal to 5.29. So there's our final answer. And then for this other one, I should also put a box around the final answer there. Okay, example 2, what is the pH of a 2.50 mole per liter solution of nitric acid? So first step first, write out your formula. Plug in your number, 2.50. And then we're going to put this in our calculator. So negative log 2.50, close the bracket, there we go. Okay, so with this here, technically you can have a negative pH. All it means is that you have an incredibly strong acid. So this doesn't happen too often, but every once in a while it can happen. So negative 0.3979 keeps on going on. So my original number had 3 sig digs in it. So that was concentration. Now we're looking at pH. So I count 3 after the point. So 1, 2, 3. There's my cutoff line. So pH is equal to negative 0.398. And that's our final answer. All right, so let's move on to how we can calculate hydronium ion concentration when we are given pH. So this is going to be the formula that we need here. Okay, so how we're going to get times 10 to the power of negative pH is like we were doing before. So we're going to do second function and then log to get that times 10 to the power of. One thing that I want to talk about that's a pretty common mistake is forgetting this negative in front of the pH. If you get a weird number, you probably forgot this negative. So don't forget the negative. And then I'm just going to write down what I said here about getting that 10 to the power of. So second function, and then log. So if I do this example, given a pH of 5.72, what is the hydronium ion concentration? So just showing you how I would put this in my calculator. First, I'm going to show you what it would look like if we didn't put the negative, so that you kind of know what the dead giveaway is that you forgot something. Okay, so let's just do it the incorrect way first. So second function log to get that 10 to the power of. Now, if we just put 5.72 and hit enter, 524,807.4602. That isn't a reasonable value to get for your concentration of hydronium. Okay, so that's kind of your dead giveaway that maybe you forgot something. So now I'm actually going to do it correctly. So second function log negative 5.72, hit enter. So now we're getting a more reasonable number. Typically, your values for hydronium concentration are going to be quite small. Okay, so 1.9054 goes on forever, and then the e to the negative 6 just means times 10 to the power of negative 6. Okay, so since our value for pH, there's 2 sigdigs right there, so 2 sigdigs. So what I do is, since this value here is concentration, I have to count from the very start because the word concentration doesn't have the letter P in it, so we need to look at the whole number. So 1, 2. So the concentration of hydronium is going to be 1.9. Now, here's the thing that's easy to forget. We still need to write times 10 to the power of negative 6, because 1.9 is not the same thing as 1.9 times 10 to the negative 6. So times 10 to the negative 6 mole per liter. Okay, what is the concentration of hydronium ions in a solution with a pH of 4.31? So let's start off with our formula. So then 10 to the power of negative pH is equal to 10 to the power of negative 4.31. So if I wrote that in my calculator, so second function log negative 4.31, hit enter. So 4.8977 keeps on going on forever times 10 to the power of negative 5. So 4.8977 times 10 to the power of negative 5. So then for sigdigs here, so we got 2 sigdigs because this is pH, so we look after the point. This is concentration, so we got to look at the whole number. So 1, 2, so 4.9. Oh, I should write this in a different color. 4.9 times 10 to the negative 5. And then concentration, you have to put your units. And I'm just going to add in hydronium concentration. So again, reminder, look at the whole number for sigdigs.